Hi, everyone. Thanks for joining. My name is Phoebe. Cassie couldn't make it today. Yeah, like I said, my name is Phoebe. I work at the Earth Institute in the Communications Department, here with my colleague, Adrian. Adrian, can you say hi?
Hi, everybody. I'm Adrian. I work with Phoebe in the Communications Department at the Earth Institute.
So we're going to be hosting today Kyle's session. So thank you so much for joining for another installment of EI Live for K-12 students and educators, brought to you by the Earth Institute at Columbia University. For those of you who are not familiar with the Earth Institute, our core mission is to foster a greater understanding of the science behind sustainability and the climate crisis and what we as global citizens can do. Experts that make up the Earth Institute include earth scientists, economists, business and policy experts, and specialists in public health and law. The Institute is made up of more than 24 research centers and several hundred people who collaborate across many disciplines and schools at the university. What we're hoping to do with these sessions is to introduce you to our interdisciplinary work through our experts. We will have sessions until the end of June for K-12 students and educators. So today we're going to hear from Kyle Fitch, a PhD candidate in the Department of Atmospheric Sciences at the University of Utah. He will be introducing us to introductory components of machine learning and demonstrate how they come together to automatically classify images of snow. And Kyle did another session last week, which you can find on the EI Live website. So today we are going to be using the Q&A box, not the chat box. So if you go down to the bottom of your Zoom window, you should see a Q&A button. As a reminder, the Q&A box should be used to ask questions or to answer the presenter's questions. We will be monitoring it throughout the talk, and once Kyle is done with his presentation, we'll go through the questions. Once the session is done, we will share a link with everyone registered for this event so that you can access the recording later on when it's posted to YouTube. Without further ado, here's Kyle.
Okay, thanks, Phoebe. All right, so what I wanted to do was provide an introduction to machine learning for those who are curious. It's becoming really common to hear about machine learning being used in several different industries, just about really in any industry today. So a lot of scientific disciplines. I'm definitely no expert in it, but I have used it for some of my PhD work. So I wanted to introduce some of the basic terms, and then I'll provide some resources at the end in case you want to find out more about it. And so there's a really wide range of different ways to do machine learning, as you can see on the right-hand side here. And so I'm just going to talk about a few of those, but really there are dozens of different ways to do machine learning. So again, I encourage you to go learn more about that if you're curious. So first off, on the left-hand side here, you can see machine learning is a subset or a subdiscipline of artificial intelligence. And within machine learning, you've probably heard of neural networks or deep learning. This is quickly becoming the most common method of machine learning. But as you can see on the right-hand side here, especially at the top, if we go to classical learning, that's kind of the type of machine learning that's been around for a few decades now. And the most common approach for that, especially in recent decades, is supervised learning, where you feed not just raw data to the machine, but you feed data that is accompanied with labels. So you'll see some examples of that. And today I'll show you some classification methods using machine learning, and we'll talk about decision trees and logistic regression, which are just two different types of algorithms that we can use in machine learning. I'll also talk about one ensemble method called random forest, which is really just several decision trees sort of averaged together. And I will also talk about neural networks and deep learning, the most common type, which is convolutional neural network. And that's very common for image classification, which is what I'm going to show you today. And both of these figures were from this blog on the lower left-hand side of the screen from again, it's just kind of an introduction to machine learning. But you can get all this information from textbooks as well, but he does a really nice job of kind of distilling the information into these figures. So machine learning, we deal with it all the time in our daily lives, whether it's autonomous vehicles or our virtual personal assistants on our phones or smart speakers. Also using Google Maps when that application makes predictions about traffic and how long it's going to take you to get from point A to B. Video surveillance, and then finally social media and ad targeting, where they're trying to offer things to you based on your interests, based on your browsing history, that sort of thing. So all of these things are using data and trying to make predictions based on that data. So in the atmospheric sciences, which is my discipline, I just kind of did a quick browsing of recent papers that have been published on that are using machine learning in the atmospheric sciences. A lot of these, as the first bullet says, there are just sort of targeted at improving models for prediction of weather and climate, kind of in general, in several different ways. But more specifically, there are some papers that are trying to do this to improve the prediction of specifically severe weather, whether that's what's severe weather look like for the next day or tornado prediction for the next hour, which would be a huge improvement because, as you may know now, anywhere from about 10 to 15 minutes is a pretty typical forecast when they issue a tornado warning. That's about all the heads up that you have. So if they can extend that warning time, that's a huge improvement. So they're looking into machine learning for that. They're looking into using machine learning using satellite and radar data, observing clouds and weather with satellite and radar data, and then again trying to better classify those clouds or the precipitation that's observed with the satellite and the radar data. Also reconstructing climate information was another recent paper I saw. And then finally, the one I'm going to talk about today is classification of cloud and precipitation particles from images, specifically snowflake images is what I'll show you today. So we can distill machine learning down into three basic components. And if you remember anything today, I think this is what you'll want to remember, because if you can kind of compartmentalize machine learning into these three components, it'll sort of help you remember how it works in general and kind of help your understanding going forward. So the first one is data. So the computer program, it has to have information to learn from. And when I say learn, I'll get into more detail about what that means, but basically we kind of have to teach the computer program what we want it to get out of that data, what we want it to predict from that data. The second one is features, or also called parameters or variables. And this is basically what aspects, what components of the data are most important, and what do we want the computer program to focus on in that, because it can't focus on every single piece of that data. It has to, so we have to kind of narrow its focus to make it more efficient. So we do that with features. And then the last one is algorithm. So how exactly is the computer program finding the best solution? And this is usually some sort of mathematical or statistical approach, or just kind of a logic sequence. And I'll show you an example of that. But if we look at the bottom here, if you're familiar with computer programming in a classical sense, when you do that, you create some set of rules for the program to follow, and then you provide it data, and then it spits out some answers. When it comes to machine learning, what we're doing is we're feeding it data, we're telling it what the answers are, and then it comes up with its own rules. And if it does a good job, it applies those new rules to a new set of data and makes a prediction from that on its own. So this is about automated prediction. So we'll get into more detail about these three basic components. So again, the first one was data. And in this case, I'm showing two different examples of image classification. On the left-hand side are some handwritten numbers. These are, this is a pretty famous set of data. If you read about image classification and machine learning, this is called the MNIST data set, and it's, I think millions, if I remember correctly, millions of these images of handwritten numbers. And so if you think about this, just when you see a number with your eyes and your brain is processing that, the number 4, for example, can be handwritten in several different ways, as we show here, but every time you see any instance of that, you know it's a 4. So basically, we want to kind of replicate that process with a computer program. We want it to be able to recognize a number. So that's what they did here with the MNIST data set. So if we feed these images into the program and we tell it this is 4, that's called supervised learning. So this is where we're telling it the answer, and then it learns from that, and it starts to make predictions on its own. On the right-hand side, we're doing that with snowflakes. So I did another presentation, as Phoebe mentioned, and I'll provide a link for that if you're interested, but this is a type of snowflake that we call an aggregate. So again, if we feed it example images of an aggregate, it can learn from that. And so if you zoom into part of this number 4 image, you can see that it's really all it is, that the data is just a grid. It's a pixel grid, right? And the pixels have different levels of brightness or intensity. So really the data here in image classification, at least in terms of these gray shade images, is just some m by n size grid, depending on how many pixels you have. And then there's a value for every single pixel that tells you how bright it is, right? So that's the information. That's really the information that we're giving to the computer program. So you might be wondering, well, how do we gather that data? And maybe it sounds simple. You just provide these images and the answers, but in reality, that can actually take quite a bit of time. This is what we call a training data set. And in order for the program to learn well enough to be accurate, we have to have enough examples. And those examples need to be pretty diverse, because it has to be able to guess the right answer based on a wide range of different examples when you provide it new data to classify. And typically, the more complex the model or the algorithm is, say like something like a deep convolutional neural network, that's pretty complex. Typically, the more complex it is, the more examples it needs to learn from. So again, this can be really time consuming. If you're trying to build a neural network from scratch, you need usually up to millions of images, but there are some ways around that, and I'll mention that again. If I forget to mention it, please ask. But for our Snowflake classification project, what we're doing is using a citizen science approach, where we teach citizen scientists the basics of Snowflake image classification. And then you can go to this website and actually look at these images of snowflakes and tell us what type you think it is. And most of the time, just with a little bit of introduction to Snowflake imagery, people are able to do pretty well at that. So we can then use that, test whether it's reliable, and then actually use that to train our models. And then that second link I've provided is the Snowflake identification presentation that I did a week ago. And I'll provide that at the end as well. So the second component of our machine learning is features. So again, this is not just, rather than just looking at all the data and every single pixel in an image, we want to be able to tell the computer program, well, what is the most important way to look at the data, right? So in the number 4 example on the left here, when you think about, well, how is my brain recognizing that that's a 4? Well, maybe it has something to do with the way that the bright pixels are arranged, right? So maybe one feature would be taking the position data. So you have, again, you have a grid of pixels, and for every pixel you have some position coordinates, say X and Y. And so if you know the position coordinates for every single bright pixel, and so you also have to sort of define, well, what's a bright pixel, because there's, you know, some of those pixels aren't quite black, but they're pretty dark. So at some point you have to define what is a bright pixel, and then you can say, how are these bright pixels arranged? And then if the computer program can look at that, then it starts to learn, oh, okay, well, if they're arranged in a certain way, then maybe that's a 4. And we also do this with snowflakes on the right-hand side. But in this example, one feature might be if you were to draw an oval around the entire snowflake, like I've done here, then you could say, well, maybe the type of snowflake is, maybe one helpful feature is the number of bright pixels divided by the total number of pixels inside that oval. And so if you start to kind of narrow down what parts of the data the program should look at or how it should look at them, then you can start to distinguish a 4 from an 8, for example. Or you can distinguish, over here we have an aggregate snowflake, distinguish that from a grapple. Because as you can see for the grapple, if you draw an oval around that, it looks like you have a lot more bright pixels than you do dark pixels. So things like that you want to start to key in on, and those become your features. And so you're telling your model, these are the features that you should be looking at. And then the third component of machine learning, which is the part that, this is where you get the dozens and dozens of different methods of machine learning, is how do you want your program to solve the problem and find the right answer? And that is the algorithm. There's several different algorithms, like I said. Here I've arranged them from left to right, with the easiest or the simplest on the left, with the more complex ones on the right-hand side. On the left-hand side, I'm just showing you a decision tree, for example. And if you think about a decision tree, we use these every day. You know, for the example I'm showing here is, well, do I have any work to do? Yes, okay, I'll stay in and I'll do my work. No. If I don't have any work, maybe, well, then what's the weather outlook? Oh, it's nice and sunny. Okay, I'll go to the beach. So that's the sort of logical sequence I'm talking about when I'm talking about a decision tree. But a single decision tree will have some imperfections. So what a random forest does is it takes a decision tree, sort of averages several decision trees together to get the best answer. And then I'll also go into more detail about that, as well as in the middle, we have a multinomial logistic regression, which might not mean anything to you yet, but I'll tell you more about that. And then on the right-hand side, we have a deep convolutional neural network, and I'll talk more about that as well. So these are technically 4 different algorithms that we've used for snowflake classification and that have been used in the past for snowflake classification. So as a classical example, because remember we have sort of classical machine learning algorithms like decision trees versus deep learning or neural network type algorithms. So this first one is a classical example, and I've sort of combined decision trees and random forests since they're pretty closely related. So what I'm showing here on the left is sort of this decision tree structure that you saw on the previous slide. And we also want to think about the last thing we talked about, which was a feature. So if we say that one of our tests or one of our questions that we want the program to ask is what is the number of bright pixels divided by the total number of pixels? And then as we train our model, it might come up with a value, the best value for that. And it might say, well, the best value for distinguishing a grapple from an aggregate is 0.75. And so that value is determined through training. So then when you feed it a new image and it gets down to this part of the decision tree, it'll do that. It'll check that. Is it greater than 0.75? Yes. Okay, then maybe it's a grapple. And so that's how a decision tree works. So if we look on the right-hand side, if we feed it an image of a grapple, then if it works well, maybe it comes down the decision tree structure and it gets to the right answer, grapple. Or maybe it chooses the wrong thing and it arrives at the wrong answer, and instead it chooses an aggregate, which is actually pretty common because, again, this is a pretty simple algorithm, and so it has some limitations to it. And so one way we can overcome that while still keeping it fairly simple, because the benefit of using a simple algorithm is if the problem isn't too complicated, then you want to keep it as simple as possible so that you understand what your model is doing. But one way to overcome this is just to use several of these decision trees and average them together, and that's called a random forest or an ensemble of decision trees. So if we look at the bottom part here, let's say the input image was a grapple, and between these 3 trees, 2 of the 3 find the right answer, well then maybe the answer that it spits out is grapple. So it's more likely to find the right answer in that case. So what we're doing here with a decision tree or a random forest is when we train the model, it's taking these input images, the data, and we're also telling it what features to look at, which again might be the number of bright pixels divided by the total number of pixels. And as it's being trained, it's figuring out, okay, what order, what sequence should I put these tests in to get to the answer, to get to the right answer? So which sequence of tests is going to have the best chance of leading to the correct answer, if that makes sense. A second type of algorithm is multinomial logistic regression, where multinomial just means that we're doing multiple classes. So instead of just grapple and aggregate, maybe we also have melting snowflakes and pristine snowflakes. So, and that's what we ended up using was 4 different classes. So if you have 3 or more classes, this is a useful algorithm. And logistic is just a sort of mathematical function. And one of the reasons that that function works well is because it gives you, if you look at the vertical axis here, it gives you a value between 0 and 1, which is useful for probabilities. So this algorithm is especially useful for determining not just what it thinks the right answer is, but how likely is it that that's the right answer. It'll give you that added information. And so that can be useful. So this logistic curve, if we have several of these logistic curves, it might look something like what you see on the right-hand side, where you have all these different data points and they're sort of separated by these logistic curves. And so when we're training this model, basically what we're doing is it's taking the data, the images, and it's extracting the features that we've told it to extract. Again, what's the best part of the data to look at, or what's the best way to look at the data? And then based on that, while it's learning, all it's doing is basically adjusting these logistic mathematical function curves. And so when it arrives at the best solution, when it's done training, it'll basically divide up the training data set in the best way possible, so that when you give it new images, it's able to find the right answer. So those are both examples of classical machine learning. Now I'm going to talk about deep learning, which you've probably heard about. It's becoming pretty common. And convolutional neural networks especially are very popular, especially for image classification like we're talking about here. And probably the main thing that makes us unique from classical machine learning is you don't have to tell it what features to look for in the data. It'll do that itself. So you just have to give it the data, preferably data that are labeled. So you can, as the example shows here, you can give it an image of a lion and say, this is a lion. So, but that's all you have to do. You don't have to worry about coming up with the best features for this model. It'll figure those out. And it's called deep because what this model looks like is, as the example shows here, it's several layers. This one only shows 5 total layers, including the input and output layers. But usually these deep neural networks are tens, even hundreds of layers deep. So deep just means there's several layers within the model where it's learning. And each one of those layers, as it moves through that model from one layer to the next, each layer is transforming the data that you've put into it, and it's transforming it into something more meaningful for figuring out what the image is, what the class of the image is. And so on the next slide, I'll show you what I mean by that. So this is a very simple example, but I think it'll help you understand what I mean by a transformation, because this is what's happening after you give it a new data set, a new set of images. This is what's happening to the data. As it's going through each layer, it's being transformed. And this is an example of a very simple transformation where, let's say you have several data points and some are white and some are black. And you notice that if you just shifted the origin of your axis up to this part of the graph, then your white dots would be completely separated from your black dots. So this is just a simple coordinate change. So by doing that, though, if you look at the last image on the right-hand side, now the model can easily identify what's a white dot versus what's a black dot. But again, this is a really simple example. These models are doing a lot more complex transformations, but this is at its very simplest basis. This is what it's doing. And so if we think about image classification, when we're feeding images into it, this is an example of what that might look like as it's going through these deep neural network layers. It's transforming the raw image on the left. And in one layer, it might do several different versions of that original image. And then in the next layer, it might do something completely different. But basically, every single layer is progressing towards the best representation of the data to figure out what is this image. And then just a few last things I want to mention about this is, of course, you need to figure out, well, how accurate is my model after you've trained the model? And in order to do that, what you want to do is minimize the error. And the error is just how far away are you from the right answer. And so that's what this is showing on the top right-hand side of the slide. Basically, if you think of this curve on this plot as your error, you're trying to minimize that error. And you're trying to find the absolute minimum. The way you do this is you tell your neural network how many steps you want it to take to get to the right answer. And you want to tell it how big of a step should it be taking. So that's basically what is being simulated in this plot on the right-hand side here. And then another thing I wanted to mention that's important for an introduction to machine learning is you also don't want to overfit your model. And what that means is you don't want your model to be trained so specifically to the training data set that when you give it a new image, it's not able to figure out what it is because it was so tuned to the training data set that it can't figure out what a new image is. And so that's what overfitting means. And an example of what that means graphically is shown on the bottom right-hand side here. So you have a collection of blue data points. If you're underfitting, well, your black curve isn't really following the blue data points at all, is it? On the right-hand side, if you're overfitting, you're following every single one of those data points very closely, which is good for that data set, but a new data set won't have the exact same data points, so it won't work well for a new data set. So the middle solution, the desired solution, is to fit well enough to the training data points that it's going to do well with the training data set, but it's also going to do well with a new data set. So one thing, again, the main thing I want you to take away from this is what are the three main components of machine learning? And so now we'll do a poll to see if you remember that. Okay, let's see how we did. So most of you are correct. It is data, features, and algorithms. So again, if you can remember that those are the three components of machine learning, then hopefully you'll remember how those all work together to use machine learning to, for my example, classify images of snowflakes. So I'll show you one example of something we've done. And so again, one model we used was a deep convolutional neural network. For that one, we used Google Inception, which is a model that has 22 layers. And so again, we talked about how each of those layers is transforming the data. And then by the time you get to the output layer, you have a model that is able to really classify new images with a high degree of accuracy. In our case, this was a 91% accuracy, which is pretty good, but it's not uncommon for neural network models to attain 95% or better. So that's why I think that they're so common and so popular, especially with image classification, is that they do such a good job of learning the data and then producing nice results. So just want to summarize what I covered here. Again, machine learning and artificial intelligence are not the same thing. Machine learning is a subset or a subdiscipline of artificial intelligence. The three components we talked about are data, features, and algorithms. And just kind of remember how those all work together. All machine learning models will have data and features, except of course the deep learning models, the neural networks, they will figure out the features on their own. And then the algorithms are widely varied. And I just showed you 3 or 4 examples of different algorithms, but there are many out there. And these are the ones we discussed, the 2 classical algorithms and then the deep learning algorithm. So that's all I had. I just wanted to provide a few links for you and some resources. So again, if you're curious about learning more about machine learning, I recommend starting with these 2 under resources, Deep Learning with Python from Cholet. And if you click on these links, it'll take you to a PDF. So you don't have to worry about buying the books. They're free and open source and available for you out there. And then the other nice one is Pattern Recognition and Machine Learning from Bishop. So yeah, I recommend starting with those 2 books, and I'm ready for any questions you might have.
Great, thank you, Kyle. We have 1 question so far. Just a reminder to everybody, if you have questions for Kyle, please enter them in the Q&A box. You should see a link to that at the bottom of your Zoom screen. Question we have here is, in your citizen scientists labeling the snowflake example, some labels may be wrong due to human error. Is there a method in machine learning to address such errors in the data?
Yeah, good question. So what we do, and I think a common approach, is to basically have a smaller data set that you can check those against. So for example, I've worked with a few undergrad students here, and we've gone through and labeled a pretty diverse set of our own images. That way we can check, so we can include those in the citizen science images and see how people do with those images. And another way that another quality control mechanism is we have several people classify the same image or the same particle. And that way we can see how high is the confidence based on, did 3 out of the 5 people pick the same class, or was it 5 out of 5? So we use sort of a threshold to control the quality that way.
Okay, great. Well, if there aren't any other questions, I guess we'll just wrap up. Thank you to Kyle and everybody who tuned in. As a reminder, we'll be sending the video around to everybody who registered to watch it later. Oh, there's one more, sorry. Can the manual error checking be replaced by machine?
Yeah, so definitely, yeah. You can, basically what you can do is take the data from the citizen science project, for example, and there's a lot of metadata. In other words, there's a lot of information about the data related to that, at least on Zooniverse, which is what we use. And so we can use the metadata as well to come up with a more automated way to figure out, how high is the quality of data that we're getting from the citizen science project. Hopefully that answers your question.
Yes. Oh, and how can you let people know how to avoid having to provide the algorithm with millions of examples?
Oh yeah, thank you. So we did this with our neural network because, again, we certainly didn't have the time or the manpower to come up with millions of labeled images. So what you can do is use a method called transfer learning. And what this is we take the Google Inception neural network model that I mentioned, and you strip off not the output layer, but the layer immediately before the output layer. You strip that off, and basically you retrain the model. And that model has been trained on images of, I think, flowers or something similar. And basically what they found in research, in machine learning research with neural networks, is if you train a model on image classification, almost all of the layers of that model are just figuring out things that are common to all images. So basically what that means is if you just strip off the second to last layer of that model and retrain it with your particular images, then it's going to do a really good job with minimal effort.
Unmute myself. What is the best path to take if you would like to study or use machine learning in your career?
So I would suggest starting with these books that I provided links to. And of course, there are others out there if you just do your own search. But yeah, I guess I would say just reading your own. There's probably classes out there if you're at a university. But really, there's a lot of information out there that you can get your hands on and teach yourself. There are courses out there as well that I've seen offered, with various costs. But there's just a lot of really good free information out there, whether it's these textbooks I've provided or even YouTube. Yeah, I will say if you do a YouTube search of neural networks, there are some pretty high quality videos that I've seen out there as well.
Great. And then I just got actually a question from Phoebe. What are the most common uses of machine learning? Is it mostly data analysis, or is there a wide usage across disciplines?
Yeah, I would say data analysis is probably the most common thing, just because every single discipline has data and a lot of data. So you may know that the job data scientist is becoming a really sought after job because there's so much data out there now, and they need people to be able to analyze that data quickly and efficiently, and to get to extract the information that they're looking for from that data. So I would say it's being a data science and machine learning are not quite the same thing, but they're very similar. And so, yeah, I think probably the number one thing is just trying to get through the petabytes of data that are out there, often specific to one single thing, and making sense out of that.
Okay. And then I have a question, actually, because I love citizen science, and I think a lot of our audience does too. Is your project focused on any particular geographical region, or could people participate from anywhere that they have snow?
Yeah, good question. So the first set of data that we've uploaded there is from the north slope of Alaska. So it's well within the Arctic Circle. So initially we were interested in snow from the polar region, from the Arctic region, but we do plan on continuing this and uploading images from here in Utah. Also, so all of these images are from an instrument called the multi-angle snowflake camera, and that's been deployed to several different locations throughout the mid-latitudes and the polar regions, including Antarctica, the Swiss Alps, New York, Colorado, so several different locations, Korea. So yeah, we do plan on uploading snow images from a lot of different locations over the next couple of years. Yeah.
Oh, awesome. All right. Well, if there's no other questions, I guess we'll sign off. Oh, see, more coming in.
Yeah.
Is there a way to tell about snow on the ground?
Yeah, that's a good question. Actually, there are some citizen science projects out there related to snowpack, which is, I think that's what you're talking about. So yeah, a lot of research being done to study once snow falls, how does that snowpack evolve over time? Because it's, you know, that solid ice is changing to water vapor over time, and it's sort of shifting and becoming more dense. And I think I have seen some citizen science projects that are out there actually doing snowpack studies. So if you look on Zooniverse, I think you might find something.
As a follow-up, like a way to tell the types of flakes, like once they're on the ground, or photograph them then, or is it only like if they're still kind of in the atmosphere or in the air?
It depends on how long it's been since the flakes have fallen, and also how high is the resolution of the imagery. So if you have a high enough resolution, you can sort of see, was this sort of a cluster of snowflakes, of ice crystals, like an aggregate, like I showed? Or is it kind of this more dense ball-shaped graupel, like, which is basically small hail? And you can see that in the snowpack, certainly right after it's fallen, no problem. After more time, probably gets a little bit harder to figure that out, just because it's kind of all melted and, you know, kind of all melded together.
Okay. I'm going to give it another minute. I feel like every time I go to conclude, we get a couple more questions. So I just want to leave it open for another minute just to see if anybody has anything else. In the meantime, how long does it take, just out of curiosity, to develop, you know, the model to start feeding data into it? And how long does it normally take these sorts of models to actually, like, to really start learning and producing results?
Well, I'd say the most time-consuming part of it is building up your training data set, because the algorithms are already out there. You know, they've already been built for you. You just sort of need to get them and sort of tailor them to what your project is. So that's not too time consuming, but yeah, I'd say the most time consuming part is building your training data set. And that sort of depends on, again, how complex your model is. So for the neural network, that's going to take more time usually. And so I've been here for almost 3 years now. And initially, like I said, we started doing this with a few different undergrad students and myself. And we were able to build enough of a training data set to get some pretty high accuracy models, but maybe not quite high enough, not quite as high as what we wanted, which is when somebody shared the idea of turning this into a citizen science project. But yeah, certainly that takes the bulk of the time. So years, I guess I would say.
Gotcha. All right, great. Well, thank you, Kyle, and thank you everybody who tuned in. We'll be continuing these sessions every Monday and Wednesday on different topics until June 29th. We have one more question.
Okay.
Can you talk about your experience about dealing with model overfitting?
Yeah, sure. So again, the best algorithms out there, they come with lots of documentation. And within the documentation, you can find out how to control for overfitting. So for example, the Google Inception model that we used, it has its own overfitting ways to combat that. So one way is to, as it gets too close to the, so like you saw the example of the data points and the curve was following those exactly. Basically what it has is a penalty function. So it's trying to minimize the error, and at the same time it's trying to make sure that it's not trying to minimize it so much that it's becoming overfitted. Hopefully that makes sense, but it really is specific to whatever model you're using. But with the Google Inception model, it's got a pretty sophisticated way to deal with that through, there's a few different mathematical functions and statistical functions that these algorithms use to control for that.
Okay, great. And I think you said that, but is it okay after this session if people have questions that they come up with, you know, after we're done? Is it okay for them to reach out to you directly?
Yeah, definitely feel free to contact me at my email there if you have any other questions. And yeah, I should be able to respond to you within a few days.
Okay, great. Well, again, we'll be doing these every Monday and Wednesday on different topics. This Wednesday's session is geared towards a younger audience than today, but next week's are both aimed at high schoolers and above. So we hope to see you again. And yeah, thanks everybody for joining in. See you later.
Thank you.